Now we're thinking a little bit about friction, and whether we're talking about kinetic friction or static friction or rolling friction, there's a pattern that all three of those kinds of a pattern that you see in all three kinds of friction. And that is, the magnitude of a friction force is always proportional to a normal force, which kind of makes sense. When two surfaces are pushing on each other harder, it's just harder for those two surfaces to slide across each other. Push your hands tight together, and it's hard to get the hands to slide across each other. But if you're pushing only very gently, then it's easy to make the two hands slide across each other. In other words, more normal force here. Each hand pushes on the other hand with a normal force. More normal force means more friction. In this case, more static friction, because it's keeping the two hands stuck. It's preventing the two hands from sliding. So there it is written algebraically, that the relationship between a normal force and kinetic friction, and then normal force and rolling friction, and the proportionality constant in both cases with Greek letter mu and then some subscript to indicate what kind of friction we're dealing with. This is called the coefficient of kinetic friction. It gives us the relationship between magnitude of kinetic friction and magnitude of a normal force, and this then is called coefficient of rolling friction. To look in detail at how those normal forces are related to the friction forces, let's just take a simple example here. I'm pulling some crate across a horizontal floor, and in that case there are basically just four forces acting on the crate: weight pulling down, and a normal force from the floor pushing up, and then my tension force pulling to the right, pulling in the direction in which the crate is moving. And then, since the crate is sliding across the floor, it'll feel kinetic friction, and kinetic friction always points opposite to the velocity. I'm pulling the crate this way, so the kinetic friction force points opposite to the direction of motion. And the magnitude of that kinetic friction force is just this coefficient of kinetic friction times this normal force. Right, this normal force comes from the floor. The kinetic friction also comes from the floor. So whenever we're talking about the normal force that's related to the friction force, that normal force and the friction force are always coming from the same surface. Remember that. That'll make things easier. And similarly, we've got a ball rolling to the right, and it's rolling clockwise as it moves to the right. And in that case, there are three main forces: weight pulling down, normal force from the floor pushing up, and then a rolling friction force that's pointing this way. If the ball weren't rolling, it would just slide across the floor left to right like this, but rolling friction is preventing sliding and causing rolling instead. So to prevent sliding this way, the rolling friction points opposite to the slide that it would prevent, and the magnitude of that rolling friction force is just the coefficient of friction times that normal force that's coming from the same surface as the friction force. A word about what these coefficients of friction mean. They're basic. You should think of them as basically a number that tells you how sticky or how rough the pair of surfaces are. Obviously, a bigger value for the coefficient of friction means the surfaces are stickier, rougher. You get more friction then for any particular amount of normal force. Let's look at a particular example here involving kinetic friction. We'll go back to the example here I'm pulling the crate left to right, and I'm pulling it. I'm giving it just enough tension so that it moves at a constant velocity. And an XY coordinate system like this, where the positive x direction is in the direction of the velocity, and we'll say that the mass of the crate is 40 kilograms, and so the weight of the kilogram, weight of the crate, mass times g, is mass of the crate 40 kilograms times 9.8 acceleration due to gravity, and that weight force then has a magnitude of 392 newtons. So those are the forces, and we know what the next step is. The next step is always write down how these forces combine to give you the net force along one direction and the net force along the other direction. Or to put it another way, give you the x component of the net force, which will just be all of the forces pointing one way or another along the x direction, and then the y component of the net force, just all of the forces pointing one way or the other along the y direction. Our goal here is to figure out exactly what the coefficient of friction is between the bottom of the crate and the floor. So in the x direction, how do the forces combine? Well, generally speaking, they always combine the same way to give you the net force. Add all the forces in the positive direction, subtract all the forces in the negative direction, and the only positive force is tension, and the only negative force is kinetic friction. So tension minus kinetic friction gives you the net force along the x direction, or the x component of the net force. And this being a net force, it's equal to mass times acceleration, mass times the x component of acceleration, to be precise. But it's moving with a constant velocity. Constant velocity means no acceleration, and if there's no acceleration, there is no net force. So if there is no net force, then certainly each component of the net force has to be zero. So this comes out to zero. And similarly, along the vertical direction, how do the vertical forces combine to give you the vertical component, the y component of the net force? It's just all the force in the positive direction minus all the force in the negative direction. And so this being a net force, it's equal to mass times acceleration. But again, there is no acceleration. So there is no y component to the net force. Now we need that number there, or rather we're looking for the coefficient of friction, which is one number hidden in here. And let's say that I'm pulling with a tension of just 100 newtons. Tension is 100 newtons. So then let me rewrite this. Tension minus kinetic friction force equals 0. Or tension is 100 newtons minus kinetic friction equals 0. So we know that the magnitude of the kinetic friction force is just 100 newtons. This backwards force is canceling out this forward force to make the net horizontal force 0. And that gets us partway to our goal. Our goal is to figure out what the coefficient of friction is in this case. because kinetic friction is just the coefficient of kinetic friction that we're trying to figure out times the normal force that's coming from that same surface, right? This normal force right here. And we can figure out what that normal force is by looking at this. Net force along the y direction is just normal force minus weight. But there is no net force. Those two forces must cancel each other out. So the normal force is just equal to the weight. And a minute ago, we said that the weight is 392 newtons. So now we can answer the problem. Now we know the numerical value of that. So we know that the kinetic friction force is 100 newtons, but kinetic friction is just the coefficient of friction times the normal force. Which in this case is going to be the coefficient of friction times 392 newtons. So just divide 100 by 392 and we'll have the coefficient of friction. And that comes out to about 0.26. No units for coefficients of friction, because when you multiply a force times a coefficient of friction, you get another force. So this is going to have units of newtons. This will have units of newtons. So this can't have any units in order to ensure that this thing has the same units as this thing. So anyway, that's how we think about friction, or at least how we think about rolling friction and kinetic friction. Static friction is a little more interesting, a little more complicated. Let's think of it this way. So imagine, again, trying to move a crate, and I pull on the crate with, let's say, think of this as a different crate, different floor. I'm pulling with 50 newtons of force, but the crate is not moving. It stays stuck. The velocity is constantly 0. Constantly the same velocity means no acceleration, no net force. To get 0 net force, it must be the case that there's some backwards force matching my pull. And that backward force is, of course, a force that prevents the crate from sliding. So if it's a force that prevents sliding, it must be static, either static or rolling friction. In this case, it keeps the crate stuck in one place, so that it would be static friction. And in that case, it must be 50 newtons of force for that static friction force. Now, imagine, and you've had this experience maybe trying to push something heavy. You push or pull, like in this example, and the thing doesn't move because static friction is fighting you. You pull harder, and it still doesn't move. You pull harder still, and it still doesn't move, because even when you pull harder, static friction is able to match the strength of your pull and cancel out the strength of your pull. So let's say Perhaps in this case, let's imagine I now, same crate, same floor, I now pull with 150 newtons of force. But now it still stays stuck. You push harder and it still doesn't move. That happens, or still doesn't move means in physics terms the velocity is zero constantly, which means acceleration is zero, which means no net force, which means there must be some backwards force that's matching and canceling out the tension. In other words, static friction can do something that kinetic friction and rolling friction cannot do. It can take on a range of values. In this example, it's able to match the strength of my pull, whether my pull is 50 newtons or 150 newtons. Whatever the strength of my pull is, it's not strong enough to get the crate unstuck. And it's not getting the crate unstuck because static friction is strong enough to match my pull, cancel out my pull, and keep the crate from starting to accelerate, to change its velocity from zero to something not zero. Well, now let's imagine instead of pulling with 150 newtons of tension, I pull just a tiny bit harder. Let's say 150.1 newtons. And that actually does get me started. It gets me started very slowly. Let's say the mass of this crate is 10 kilograms. That means now, since I am able to accelerate the crate, the static friction force can no longer match my force. The static friction force can get this big, but it cannot get this big. It can match and cancel out that force. It cannot match and cancel out that force. So we can say that the static friction force takes on a range of values up to some maximum. And that looks like the maximum, because get just a tiny bit bigger than that, and the static friction force isn't strong enough to match and cancel out that, even though it could match and cancel out that. So there's a maximum possible static friction force of 150 newtons in this case, in this example. And here's where that relationship between normal force and magnitude of a friction force comes in. We've seen that static friction force, unlike kinetic friction, unlike rolling friction, can take on a range of values up to some maximum. And the way we would say that algebraically is like this. The actual static friction force could take on any range of values, starting with something tiny, just barely larger than zero, up to some maximum value. It could reach that maximum value, but it's not going to get any bigger than that maximum value. And that maximum value is directly proportional to the normal force. It's coefficient of static friction times the normal force. So that, and of course, remember that normal force is coming from the same surface that is the source of this friction force. So we've still got the weight of the crate, and we've still got the normal force from the normal force from that surface, the floor. But in this particular case, when I just barely start to get that thing moving, what's the, how much is it accelerating? How fast is it accelerating when I finally pull hard enough to change its velocity from 0 to something a little bit bigger than 0? Well, use Newton's second law as always. And we'll say that the net force horizontally is just all the forward force, my tension, minus all the backwards force, which will be the maximum possible value of static friction. I'm pulling now just barely hard enough to overcome static friction. And of course, tension, now I'm pulling with 150.1 newtons. And that maximum value of static friction is just plain 150 newtons. So, so the difference, the net force accelerating the crate forward is a pretty tiny net force, just 0.1 newtons. But being a net force, it's equal to mass times acceleration. And the mass in this case was 10 kilograms. So divide both sides of that equation by 10 kilograms to get the acceleration, and you will get this divided by 10, which is 0.01 meters per second, or if you want a number that doesn't feel quite as small, that's the same as 1 centimeter per second. The crate is gaining 1 centimeter per second of speed in every second. 1 centimeter per second of positive velocity is added on in every second. So that's an example. And then in this case, how would we find the coefficient of static friction? Well, to find the coefficient of static friction, you need to know the maximum possible value of static friction, because the only place coefficient of static friction appears is in the equation for maximum value, maximum strength of static friction. Maximum value of static friction is just coefficient of static friction times the normal force. We've just determined that the maximum magnitude for static friction is 150 newtons. And that's for a crate that has a mass of 10 kilograms. The two vertical forces, normal and weight, must be canceling each other out in this case because vertically speaking, nothing is happening. Or to be more precise, vertically speaking, there is a constant vertical velocity of 0. And again, constant vertical velocity means no vertical acceleration, which means no vertical net force. Which means these two have to cancel each other out, so they have to be equally strong to cancel each other out. And that weight is just mass times g, 10 kilograms times 9.8 meters per second, or 98 newtons. So 98 newtons is the weight, which will also be equal to the normal force in this case. That normal force coming from the same surface as the surface that provides the friction. So a 98 newtons goes in there, and then we can solve for the value of the coefficient of static friction. 150 newtons, that was the maximum value of static friction, equals coefficient of static friction times normal force, but the normal force is 98 newtons. And so in this case, coefficient of friction is 150 newtons divided by 98 newtons, about 1.5, which when you get used to seeing a whole bunch of different numbers for coefficients of friction, that's a very, very sticky, rough surface. So you'll see more of this in class.